good. I met Franco when I had just finished the introductory part of my undergraduate studies. And I had no clue what field to choose to specialize. So one semester I decided to take all courses that were offered by the university. And there was one course that was really outstanding. And that was given by a young Italian professor. About the age that we could see in the poster of the event. And Franco made this course, this was on the nuclear shell model. And he made that course, it was incredibly easy. Nuclear physics was easy, beautiful. And the second part of the course was on the atomic boson model. Something new, very new at that time. And I remember still the excitement that I felt when after one of the courses I went to the library. And I just flipped through some of the journals. And there I saw a paper by Franco. And it's just the material that we had been taught that same day in the course. So this I felt, and this brought the research much closer to us, because usually when you start studying physics, they talk about things that were done 2 centuries ago, 3 centuries ago. But so this was this course really brought, this was the first course that talked on actual research that was going on at that time. So this for me was very stimulating, I was very excited in what I did after that. Thank you very much. As a title of this talk, I chose some work that is related to the last paper that I wrote together with Franco, which was on a 2-component model to study the form factors, the electromagnetic form factors of the nucleon, of the proton and the neutron. So, and this has, the title of the talk is it's on the strange properties of the proton. How important are the strange quarks in the proton? This work, well, I will discuss 2 calculations that we've done, the 2-component model and a more recent one that was published this year in collaboration with Jacopo Ferretti and Elena Santopinto, who both are here. Jacopo Ferretti recently got his PhD in Genoa and is now a postdoc at Milan. So that the proton is not an elementary particle as it has been known for a very long time, since the measurement of the anomalous magnetic moment. Here I've listed the whole set of important developments, the spatial structure, which was revealed by Hofstadter in the 50s, the quark structure, etc. More recent ones are the flavor asymmetry, that the proton has more anti-d quarks than anti-u. There's the issue of form factor ratios, the ratio of the electric to magnetic form factor. And in the last 10 years or so, was the measurement of the importance of strange quarks in the proton. So I will concentrate on the last issue. So why is this important? See, the strange quarks, they can only come from the sea. Because the proton, the valence quarks, it's 2 quarks, 2 up quarks and 1 down quark. So if there is any strangeness in the quark, it has to come from the C quark. Yeah, so this is a unique signal of the importance of the C quarks in the description of the proton. The interest these days is there have been a new set of experiments which use the parity violating part of the electron scattering, and these are collaborations of sample and debates. Happens at G0 at Jefferson Lab and A4 at Mainz, in which they've been able to uncover the importance of the strangeness in the proton. So, how is this measured? So we do electron scattering of the proton, and you can either exchange a photon or a C boson. So this is an electromagnetic process, and this is a weak process. The difference is the parity. The electromagnetic process conserves the parity, and the weak process violates the parity. So if you have a method in which you can measure the parity violating part here, we can combine it with the electromagnetic part to get a handle on the importance of the U, the D, and the S quarks to this process. Okay. So how do we describe this? This is the nuclear matrix elements of the vector current. The vector current can be either the electromagnetic or the weak one. There are some form factors here that's called F1 and F2. That carry the names of the electron powder, or more usual ones that are used as Sachs form factors, which are related to the other ones by some difference. Yeah, so this V can either be electromagnetic or the weak process. And then each one of these currents, we can make a flavor decomposition. Yeah, for example, for the electromagnetic one, for the proton, it's the factors here, 2/3 and minus 2/3 are just the electric charges of the quarks. For the neutral, we have something similar. We use here the charge symmetry. In this way, the neutral weak current can be written in this way, and here we have the weak charges. So the corresponding form factors obey the same type of relations here, the same charges here and the weak charges here. So now we can let's see if we can measure the electromagnetic form factor of the proton, the electromagnetic form factor of the neutron, and we combine it with the weak form factor, let's say of the proton. We have three pieces of information, and then we can invert these equations to get the contribution of the U, the D, and the stage quark. And that is usually what is done. So here, here's the result. So the strange contribution is a linear combination here of these three processes. And what is measured in these new experiments, the parity violating part, is this one here. Okay? Is the weak form factor. And then it is combined with the electromagnetic form factors, which already have been known, and so this can be used to get a handle on the stage. And this, to use this method, was first pointed out by Bob McHugh and Beck in '89. The quantities that I will discuss today are the static ones. One is the magnetic moment, which is simply the zero of the magnetic form factor. And the other is the charge radius, which is the derivative of the electric form factor in the origin. Yeah? And then I will look here only at the contribution to these variables, the magnetic moment and the radius by the strange parts. This is a figure that we will see a couple of more times in this part. So this is kind of an overview of the different predictions of the theoretical models. So all these red points are theoretical calculations. Yeah? So this is the strange radius with the strange magnetic moment. And these were theoretical calculations in which there was no guidance by experimental results. So these calculations, most of them were done before the experiments. Yeah? And so we see that there's a large spread in predictions. Also, although there is there's some clustering here for very small values of the strange radius. For the magnetic moment,